All right, learning objectives for this segment. Define enthalpy and its relation to work and energy. Relate changes in heat and work to changes in system energy and enthalpy. So that's what we'll be covering, especially this idea of enthalpy and what that is. So remember, one of the important ways that energy is transferred between systems is as heat. If you have a hot system and a cold system, then heat will be transferred from the hot system to the cold system. The blue system gains energy and the red loses energy. So in this case, the heat transfer into the blue system is positive, and the heat transfer out of the red system is negative. We saw some examples of that in an endothermic reaction that you saw in the last lecture segment. Then the cold system is an endothermic reaction because as the change of the energy was lowered by the balance being broken and formed, the energy was transferred into the system and Q was positive. For the exothermic reaction, the thermite reaction, then the energy was less than zero. Sorry, the heat transfer was less than zero. Q was less than zero because it transferred heat to the environment. Okay, so energy versus enthalpy. So what are the differences between them? So let's take a situation. How much heat is transferred to the system when a reaction occurs at constant pressure? So we have a reaction that's occurring. Something could happen with the volume. We don't know what, but it remains under a constant pressure the whole time. So let's go to first law. Let's look at that. So the energy, delta E, is always the work plus the heat. The change in energy is equal to the work transferred plus the heat transferred. And now we're going to call that, we're going to say that this is, I'm going to write it the other way because it'll make it easier later on, Q plus work, just to keep things in a nice order. Right, so I'm going to call this the QP, the heat at constant pressure. You could have a change in energy. You can have some very different heat transfers if the pressure is not constant. So we'll say the heat transfer constant pressure, and minus P dV, P, and we don't need to make it a differential, P dV. If the pressure stays the same the whole time, then we can just write down that the change in pressure is minus P dV. And so let's rearrange this. We see that QP, the heat transfer at constant pressure, is going to be delta E plus P dV. And so let's call this, so this is interesting here because we have the heat on the left side, and on the right side we have all state variables. The energy is a state variable. And so the change in energy depends only on the initial and final state. The volume is a state variable as well. The volume of a system doesn't depend on how it got to that volume. It just depends on the volume. And the same with the pressure. The pressure of a system only depends on the configuration of atoms. It doesn't depend on how it got to that. So it's very interesting. So let's call this whatever's on this side is looks like it's the difference of state functions. Let's call, or we'll have a label, call H, just call it H for now, E plus PV, so that we'll label it as H, call that the enthalpy. We'll just make this definition. So delta H will be H final minus H initial, and so delta H, so it will be E final plus P final V final minus E initial plus P initial V initial. So that would be delta E plus, now P final and P initial are the same, so this is just going to be pressure times V final times V initial, so delta V. And that is just equal to QP. So we see that at constant pressure, the heat transferred at constant pressure is actually a state function. Not the heat in general is not, but if a process happens at constant pressure, then the heat is a state function. It's a state function. Let's give it a special name so we don't get confused about whether it is a state function or is not. We'll call it the enthalpy. So E plus PV is the enthalpy. It is a state function. And it turns out, if you're carrying out reactions at constant pressure, it's easier to keep track of the enthalpy than the energy. Because if you look at the heat that comes out of the system, as long as you keep it under constant pressure, what you get out is the enthalpy rather than any other quantity. So it has a special name. Since most reactions occur at constant pressure that happen in everyday life, it's we want to keep track of the enthalpy. It's easier to measure the enthalpy and the energy. It's sort of hard to, if you want to calculate the heat coming out and the volume change, then that's sort of a mess. But enthalpy is easier. We just need to keep track of the heat. And that's the key. The heat transferred at constant pressure is a state variable called the enthalpy. So that's why we care about the enthalpy. It's just easier to keep track of. All right. So we've got a new definition of the enthalpy. Okay. The following reaction has a change of energy for the system of minus 10 kilojoules. What are the work and the change in enthalpy that occur? Well, this occurs under constant pressure. So the change in enthalpy is just going to be equal to the heat transfer from the perspective of the system. The work is minus P delta V. Let's make this clear. Delta V equals 20. Let's make it explicit. It's minus 1 atmosphere minus 20 liters, because it's shrinking, equals 20 liter atmospheres, 0.101 kilojoules per liter atmosphere. That cancels. We get 2.025 kilojoules. And delta E equals W plus Q. Q is equal to delta E minus work, but that's just saying that delta H is equal to delta E minus work. And so delta E is minus 10 kilojoules, and the work is 2 kilojoules, so minus 2 kilojoules minus 12 kilojoules is the change in enthalpy of the system. Now, this is the problem we just did before. Now we're just properly labeling that the Q, the heat transferred, is equal to the change in enthalpy of the system. So the heat transfer, the change in heat from the perspective of the system, that it's negative heat, that's losing that heat, is the same as the change in enthalpy. The change in enthalpy of the system is minus 12 kilojoules because it has lost 12 kilojoules of heat in a constant pressure process.